exist a unique integer q and r satisfying that a equal to bq plus r. Here the condition for r is that it should be strictly less than b and it is greater than or equal to 0. Now here a is a dividend, b is a divisor, q is a quotient, r is a remainder. Let me take a simple example to know very clear about that. Here I'll divide 6 by 2. How do we do? We start dividing 6 by 2 like this. 2 3 is a 6. Right? Here this is a r and this is a dividend, that is a. This is a divisor, that is a b, and 3 is a quotient. How do you verify this? This verification is like that: dividend equal to divisor into quotient plus r. This is the lemma. Understood? Here we generally use this lemma to find the HCF of any two given integer. The steps are to find the HCF of any two integer is that first we need to apply this lemma, that is general formula a equal to pq plus r. So keep in mind that always choose a as a bigger number from the given two integer. Here the given two integers are 6 and 2. Here we have taken 6 as a, right? The bigger number as a and smaller number as b. That is a main point to know. So if r equal to 0 in the second step, here r becomes 0 in the second step, right? So there only we need to stop. Whatever may be the b in that step, that is a HCF of two given integer. Here b is a 2, so that the HCF of these two number is a 2. If r is not equal to 0, that is remainder is not equal to 0, in the step 3 what we should do? Replace that b as a and r as a b in the next step. Follow the same procedure step 1 to in this here. So repeat until remainder become 0. This is a steps to find the HCF of any two given integer by using Euclid division algorithm. Understood? Let me take one example. Here it is, that is to find a HCF of 135 and 225 by using Euclid division algorithm. First we need to choose a and b from these two integer. Here bigger number is a 225, take it as a. Here smaller is a 135, take it as b. So apply the division lemma, that is a equal to bq plus r, right? A is a 225, b is a 135. When we divide 225 by 135, so 135 to is a 270, right? It's more than this, so we take only by once, that is 135. So the remainder in this step we remain with 90. Here remainder is not equal to 0, right? So what we should do? We move on to the next step. In the next step, this is a r, this is a b, right? This b becomes a here, this r become b in the next step. So again do the same thing, that is divide 135 by 90. 91s are 90. Here the remainder is 45. So again in this step also remainder is not 0. So move on to the next step. In the next step, same thing, b becomes a, r become b. So here by dividing 90 by 45, we get 45 2s are 90. In this step we get our remainder as 0, right? So this is a step to stop. Here b is what? 45. Whatever may be the b in the step when we got r as a 0, that is a HCF of two given number. Here see, this is a HCF of these two number, 45. Understood? This is a steps to follow the lemma to find the HCF. Here some problems are there for you. You do yourself and let me know answers in the comment box. Okay. So next main theorem is that fundamental theorem of arithmetic. This theorem tells that every composite number means what? Those numbers which have common factor other than 1 and the number itself. Those numbers are said to be composite number, right? composite numbers can be written as product of primes. Primes means those numbers which do not have any factors other than number and the 1 itself. Those numbers are said to be primes, right? Composite numbers are written as product of primes and that is unique. This is the theorem statement. That is, any composite number can be written as the product of prime and this factorization is unique. Let me take a simple example. 12 is a composite number, right? Because it has a factors other than 1 and number itself. It has factors as 1, 2 and 3 and 4 and 6 and 12 itself, right? These are the factors of 12, so that it is a composite number. How do we write this 12 as a product of prime? We need to divide by using only primes. So smallest prime is a 2. 2 is the smallest even prime. Other than 2 there are only odd primes, right? 2, 6 are 12. Again take 2. 2, 3 is a 6. Here we can't take 2 because it is a 3. Go for next prime, that is a 3. 3 1 is a 3. These are the primes of this 12. 12 can be written as product of primes, that is 2 into 2 into 3. Okay. This is also can be written as 2 to the power of 2 into 3 to the power of 1. This is a product of prime and this factorization is unique always. This is the statement of this theorem. Here one more example is there. 3600 can be written as the product of prime as like this. So let me see how do we get these. When we divide this 3600 by 2, we get 1800. Again when we divide this 1800 by 2, we get 900. When we divide this 900 by 2, we remain with 450. Here we use 2, 2 2s are 2 2s are 2 5s are. Here we can't proceed with the 2 because this is a 5 at unit place. We move on to the 3, 3 7s are 21, 3 5s are 15. Here we can take 3, 3 2s are 6, 3 5s are 15. Here we take 5, 5 5s are 15. Again lastly this is a 5 1s are 5. Understood? These are the primes of this composite number. That is 2 is how many times here? 4 times. 3 is how many times? 2 times. 5 is a 2 times. This is a product of primes for this particular composite number. Understood? Here next we need to know about HCF and LCM. So what is HCF? HCF is a product of smallest power of common prime. Keep in mind that is smallest power of common primes. Here greatest power of all prime factors. This is a main difference between HCF and LCM. In HCF we consider only smallest power of the common prime factor from those two integers. LCM is the greatest power of all the primes. Okay, let me take one example here. Here we need to find the HCF and LCM of these three integers 12, 15, 21. So what we can write 12 as a product of prime as 2 into 2 into 3. That is a 2 2 is a 4, 4 3 is a 12. We can do like this. 2 2 6 are 12, 2 3 is a 6, 3 1 is a 3. This is we written here. Right, that is 2 is twice, 3 is once. Similarly for 15 this is a product of prime. Here for 21 this is a product of prime. For HCF we consider the smallest power of common factor. First we consider which is a common factor from these three, which is 3. Here 3 is there, here also 3 is there, here also 3. First we need to write 3. Later consider the smallest power from these three is a 1, right? This is a HCF. For LCM we need to consider every prime factors. Here the prime factors are we taken as 2, 3, 5, 7. So later we move on to the powers. Here we consider greatest powers. The greatest power for 2 is a 2, for 3 it is 1, for 5 it is 1, for 7 it is 1. Understood? By multiplying these we get 420 as a LCM. Clear? This is about HCF and LCM. Okay, one more property is there, that is HCF into LCM of any two given integer is equal to the product of those two integers. Here we take 12 and 15. Understood? HCF of these two is, this is common factor from these two is 3 and smallest power is 3 only, 1 only, that is 3. Here LCM for these two is, first we need to write every prime factor, that is 2 into 3 into 5. Later we consider the highest power, that is 2 to the power 2, 3 to the power of 1, 5 to the power of 1. By multiplying we get 4 3 is a 12, 12 5 is a 60. So by applying this property, HCF is 3 and LCM is 60, which is equal to product of those two integers, that is 12 into 15. Here this is also 180, this also 180. Understood? This is a property. So here some theorem is there, we need to keep in our mind, because it is very useful to use. It can be used in the next theorems. Okay, so that the theorem statement is that if P is a prime, if P divides A square, then P also divides A. That is, if P divides A square, then P also divides A. This is the statement for this theorem. This property for HCF LCM is already we have seen this, that is product of LCM and HCF of any two integer is equal to the product of those two integers. One more corollary is there, if P divides A cross B, then it implies P divides A or P divides B or both. Okay, this is the corollary. So here one more example is there for you. Find the HCF and LCM of 6 and 20 and verify by using this formula. Okay, you can do by your own. Here we have irrational numbers. We all have know about that. What is irrational number? Irrational number is those numbers which cannot be written as P by Q form. Okay, here condition is that Q should not be 0 and P and Q are the integers. Those numbers which cannot be written in the form of P by Q, those numbers are said to be irrational numbers. Where P and Q are the integers, Q should not be 0, because if P 0, Q 0, then anything by 0 becomes not defined, that is infinity. Okay, so that Q should not be 0. Here example for irrational are square root of 2, square root of 3 and square root of 5. Whatever may be the number prime in square root, those are the irrational numbers. Okay, here 2 is a prime, 3 is a prime, 5 is a prime, square root 7 also irrational, square root 11 also irrational, square root 13, square root 9 is not, because 9 is not a prime, right? It is a odd number. 17 also irrational number. Pi is also irrational because the value of pi is 3.1417, like something like that. It is not repeating, not terminating. So also we can state this as those numbers which are non-repeating and non-recurring, also the irrational numbers. Here the real numbers consist of rational and irrational numbers. Irrational numbers are these, and in rational numbers we may see integers. In that integer, natural number is a subset of whole number, is a subset of integers. This is about number system. Next is here we know that any number in any prime number in the square root is a irrational number, but we need to prove by theoretically. How do we do? First we need to we can prove by taking contradiction. The contradiction means first we need to assume that square root 2 is a rational. If square root 2 is a rational means we know that every rational number can be written in the form of p by q form, right? If square root 2 is a rational, means it can be written in the form of p by q. Assume that p and q are the co-primes, that is this is in the least form. You need to assume. So squaring on both sides, we get 2, squaring on both sides and rearranging, we get 2q square equal to p square. This is p square equal to 2q square. Right? Here 2 divides p square. It means p also divides p. Already we have seen one theorem, that is if p divides a square, then p also divides a, right? So that 2 divides p. It means how do we write? P equal to 2m, right? Take some pm as some integer. Here it shows p divides, 2 divides p. Okay? Substitute this p value in this, again we get 4m square equal to 2q square. Cancelling 2 on both sides, we remain with 2m square equal to q square. We can write it as q square equal to 2m square. Okay? So see here, 2 divides q square here. It means, it implies that 2 also divides q. That is 2 divides q. Okay? So by seeing this one and this statement, that is p divides 2, 2 divides p here, 2 divides q here. It means 2 is a common factor for both p and q. Am I right? Yes. Because we have proved that 2 is a common factor for p and q. Is it possible? No. Because already we have taken that p and q are the prime here. PQ are co-primes. Co-prime means there should not be any common factor for these two. But here we got 2 as a common factor. Is it not possible, right? So that our contradiction is wrong. Whatever we have assumed that square root 2 is a rational is a wrong here. Assumption was wrong, therefore square root 2 is a irrational. Understood? This is the process to prove that given number is the irrational. Here some 3 examples are there for you. You can do by yourself. Same procedure you can follow. Here we need to prove that square root 5 is a irrational number. So first we take by proving by a contradiction, that is first we assume that square root 5 is a rational, so that it should be written in the form of p by q. Same process whatever we have done for square root 2, you can follow for square root 5 and here also. Okay? Here decimal expansion for rational numbers. In rational number we have two type of decimal expansion, that is terminating decimal expansion. One more is a non-terminating repeating, and if non-terminating non-repeating, then it is a irrational number. Okay, how do you find if given a rational number is a terminating or non-terminating repeating decimal? But just by seeing the denominator of that rational number, we can say whether it is a terminating or non-terminating repeating. Let me see how. If denominator has only factor of 2 or 5 or both, then it is a terminating decimal. Here 7 by 8. But condition is that it should be in the least form. Least form means these two p and q should be co-primes. Okay, this is the condition. Here 7 and 8 are the co-primes, so that 8 can be written as 2 to the power of 3, right? It means denominator has a 2 as a prime, so that it is a terminating. Or we can say that any number, any rational number p by q, if it is a simplest form, has a terminating decimal if and only if the prime factorization of q, that is the denominator, is in the form of 2 to the power of n and 5 to the power of m. Here it can be written as 2 to the power of 3 and 5 to the power of 0, because the value becomes not changed here, so that the denominator has 2 and 5 as a prime, so that it is a terminating. Here also 3 by 5, it is also in the form of this. right? If it has 2 and 5 are both in the denominator, then only it is the terminating. If not, then it is a non-terminating repeating. Simple. Here we see 1 by 3. Here it is not 2 and 5 in the denominator. It is a 3. It is other than 2 and 5 as a prime in the denominator. So that it is a non-terminating. So we can see the decimal expansion for this is 0.33333. It continues like this only. You can write it as 0.3. It is non-terminating, but it is a repeating. This 3 is a repeating. Okay, this non-terminating repeating decimal it is. In this case also 1 by 7. Here see in denominator we don't have 2 and 5 and both. We have other than 2 and 5 in the denominator, so that it is a non-terminating repeating. The decimal expansion for this is 0.142857. This repeats here 142857. Understood? This is a difference between terminating and non-terminating decimal expansion. Here some of the example is there for you. Without doing long division method, you just by seeing the denominator, you should verify whether it is a terminating or non-terminating repeating decimals. Here 3125 is there in denominator. It can be written as 5 to the power of 5. In denominator we have 5 as a prime, so that it is a terminating. Here also 8 can be written as 2 to the power of 3, so that it is terminating. Here 1600 can be written as 2 to the power of 6 into 5 to the power of 2. It means it is in the form of 2 to the power of n into 5 to the power of m, so that it is a terminating. Here also it is in the form of 2 to the power of n into 5 to the power of m, so that it is terminating. But here 455 can be written as 5 into 7 into 13. In the denominator we have other than 5 and 2 as a prime, right? So that it is non-terminating. Here 343 can be written as 7 to the power of 3. It means it is also not terminating but repeating decimals. Understood? This is about this chapter. So in this we learnt Euclid division lemma, that is for any given integer a and b. The statement for this lemma is a equal to b cube plus r, where r should be less than b and it should be greater than or equal to 0. Fundamental theorem, that is every composite number can be written as product of prime and that factorization is a unique. Next is a irrational proof, that is we know that any number in square root prime is a irrational number, but we have learned that how do we prove theoretically, by taking contradiction, which is a algorithm, that is Euclid division lemma. Repeatedly by doing this until when we get r as a 0, so at that stage b becomes the HCF of those two given integers. And one more property we learned, that HCF into LCM, multiplication of HCF into LCM of any two given integer is equal to the product of those two numbers. Okay. Terminating decimal. So but just by seeing the denominator of any rational number, then we can differentiate whether it is a terminating decimal or non-terminating repeating. If denominator is in the form of 2 to the power of n into 5 to the power of n, then it is a terminating decimal. Understood? This is about the real number chapter. I hope all of you understand, and let me know all the problems which I have given you to work by yourself. So let me know answers in the comment box. Thank you.